What is fatigue? In all honesty, fatigue is one of the phenomena in engineering that is not easily understood. What we do understand is that it relates to damage phenomena induced by a large number of load cycles, and that all the load cycles may be well below the ultimate strength of the material. Damage implies permanent degradation of material and structure, reducing the structural strength, eventually leading to failure. But how should we characterize that? Initially, fatigue has been presented using Wöhler curves, named after August Wöhler. This German engineer performed many tests and plotted the failure life against the stress amplitude. His reasoning was that the stress amplitude was most decisive for failure. This means that he observed that changing the mean stress of the cycle has less of an effect on the failure life. Because one can think of many combinations of mean stress and stress amplitude, these Wöhler curves, or AEASM curves, are generally plotted for a specific mean stress. So the curves illustrated here each relate to a certain mean stress, and they illustrate how life increases if the stress amplitude is decreased. The higher the curve, the lower the mean stress. Or, if we look at the horizontal line in this illustration, the lower the mean stress, the longer the fatigue life. The question is, can we understand this? Why would the fatigue life decrease if the mean stress is increased? One way of looking at the fatigue phenomena is through physical principles of energy. The application of cyclic loading implies that the material or structure cyclically deforms. This combination of load and deformation relates to work applied to a structure or material. Increasing the mean stress while maintaining the stress amplitude evidently implies that more work or energy is applied to the structure. Applying more cyclic energy obviously should result in more degradation or damage, and thus a shorter life. Similarly, maintaining the mean stress while reducing the amplitude stress implies reducing the cyclic work applied and hence an increase in fatigue life. The AEASM curves illustrated here contain two asymptotes. The upper asymptote relates to the ultimate strength of the material. The static test effectively is then treated as a single fatigue load cycle. The lower asymptote is the fatigue limit. This means that cyclic loading below this limit does not cause any failure of structure or material. In a previous video I explained that ductile materials are less sensitive to notches. Now this can be illustrated here with the two AEASM curves, where the upper asymptote effectively is the same for both unnotched and notched materials. There is however an effect visible on the lower asymptote. In fatigue loading with low amplitude stresses, the entire notch vicinity remains mostly linear elastic, which means that the sensitivity to notches is observed. This is illustrated by the lower fatigue limit for notched materials. The reduction of the fatigue limit can be calculated by taking the fatigue limit of unnotched material and divided by the stress concentration factor Kt. What can be concluded from this illustration is that at the same amplitude stress, a notched material has a lower fatigue life compared to an unnotched material. Although different in detail for the various engineering materials, one in general can identify several stages in the fatigue life. Take for example metallic materials, where fatigue damage first nucleate at the microscopic level to form a micro crack. This then develops further to a crack visible at the macroscopic scale, eventually leading to failure. Traditionally, the lifetime until micro crack formation is referred to as the initiation phase, while the macroscopic crack growth is referred to as the crack growth phase. In general, when fatigue testing an unnotched metallic material, the initiation phase covers most of the entire fatigue life. Once cracks can be observed, the lifetime until failure is very short. In designing against fatigue, this means first of all that one has to avoid or limit stress concentrations as much as possible. Furthermore, one should avoid any damage initiated by creating smooth, undamaged surfaces. Nucleation of fatigue cracks generally occurs at the material surface. Reducing surface roughness increases fatigue lives in general. Another important measure against fatigue is the selection of fatigue-insensitive materials. One may give in on the ultimate strength of a material, with the benefit of having substantially larger fatigue lives. The damage-tolerant design approach may increase the operational life of a structure effectively. By scheduling inspections, detecting cracks and repairing upon detection, structural life may be extended beyond the component's fatigue life.